David Herring is an award-winning science communicator with 30 years of experience working within the Earth system science communities at NOAA and NASA. David is chief of the Communication, Education, and Engagement Division within NOAA's Climate Program Office, located in Silver Spring, Maryland, where he also serves as program manager for the NOAA Climate.gov and U.S. Climate Resilience Toolkit websites. So there's more about him, of course, on the website. And we are going to be breaking this presentation into two as we kind of work to develop what we would talk about today. We realize there's a lot. This is going to be a part one. And I just want to, at this point, turn it over to David. And I'm just so very glad you're here. So go ahead.
Thank you, Rashinda. Thank you for that kind introduction and the warm welcome. It's great to be here with you and with everyone. Thank you for your time this afternoon. So, well, before I jump into the presentation, I'll just do a shameless plug for the websites that Rashinda mentioned. Here is the NOAAclimate.gov website. The name is the address, so if you want to go find it online, you can at NOAAclimate.gov. There's a magazine called News and Features. It's a popular science magazine about climate. There's a maps and data section, a section for educators, and an outlink to the Resilience Toolkit. And we have things like the Global Climate Dashboard, which is a data-driven readout on the state of the climate system. And if you click on the toolkit, it'll jump you right on over to the U.S. Climate Resilience Toolkit, which you'll notice is not a NOAA-branded site because it's a full partnership with all of the U.S. federal science agencies of the U.S. Global Change Research Program, including NASA, U.S. Geological Survey, EPA, Department of Energy, and many others. So, but my team also hosts and curates the toolkit. And so those are some online sources of information that you can come back to, and I'll reference them to some extent in my talk. And what Rashinda and I discussed is that maybe I'd spend a little bit of time today laying out some basic sets of information, and then we would try to allow plenty of time for discussion and Q&A. And of course, I want to go ahead and encourage everyone to stop me and interrupt me if you have questions or if something's not clear. Definitely do take a moment to let me know that. So just briefly, a little bit about myself. I am a science communicator, as Rashinda mentioned. I'm also a person of faith. I am a follower of Jesus Christ, and I have been a member for the last 20 years or so in our local United Methodist Church here in Bowie, Maryland. And I'm one of those people who believes very firmly that we can be both. We can have both. We can be a person of faith and a person of science. I don't believe those things are mutually exclusive. And so when Rashinda reached out and invited me to join you guys, I was eager and to jump at the chance. So thanks again for the warm welcome. So today we're going to talk a little bit about sea level rise. Why is it happening? What are the impacts and implications of that? And what can we do about it? And as Rashinda mentioned, we'll follow up on March 21st with a look at some of the psychology and social science about engaging people in action. So today it's just causes and effects and a little bit about what we can do about it, with lots of discussion and conversation with you all. And then about 1 month from today, we'll zoom in on some of the social science research, some communication strategies, and maybe some sample case studies of communities taking action. So with that, let's jump on in to part one. You probably already know, but in case you weren't aware, sea level, when we talk about geologic time, has always been changing. It's continually changing. And so as our world has gone into what are called glacial maximums or ice ages, and then interglacial warm periods, sea level has waxed and waned by quite a lot. And so a lot of that has to do with the fact that a lot of the world's water gets locked up in these ice sheets on Greenland and Antarctica. So the more those ice sheets melt during the warm periods, the more that water runs into the ocean. And of course, the more the ice sheets build up, the more of the water is trapped and held in these vast ice sheets, and then the lower, the sea level. So you can see in this map on the left that about 5 million years ago, the North American coastline looked very different than it does today. And you can see during towards the end of the last glacial maximum, or ice age, sea level was much lower, and this blue line is showing you roughly how far out you had to go to get to the shoreline. And this chart on the right here is showing you in meters, so a meter being a little over 3 feet, how much sea level has changed. So as we've gone into and out of glacial maximums or ice ages on roughly 100,000 year cycles for about the last 2 million plus years, you can see how much sea level will have changed. Now, it might look like, wow, this is changing a lot and it's changing really fast, but these are geologic time frames, so very long periods of time by human lifespans. But, in terms of the Earth's age, these are relatively rapid changes. So it takes about, about 40,000 years to cool down into an ice age, and about 5 to 10,000 years to warm up out of an ice age, which geologically speaking, that's pretty fast. But in our lifetimes, that's pretty slow. So zooming in more recently in time, you can see that according to this chart, it's showing you what the current level, sea level, average global sea level is as compared to during the last glacial maximum. And for about the last 8,000 years, sea level has been fairly static. And what's really interesting about this period, this plateau up here on this chart, is this is the period of modern human society, modern human civilization. So you could say that our systems, our travel systems, the coastal communities that we've built, a lot of the trading were happening out of port cities. So a lot of human population, a lot of human cities and built environments are in coastal communities. And those communities were developed and optimized over this period of time, when from a human standpoint, sea level has appeared to be fairly static. That's an important point to keep in mind. So you might be wondering, well, how do we know what sea level is today? How do we know that it's changing today and how fast it's changing today? How do we know that it has changed or what it has been in times past? So when we look at geologic time, we have a lot of proxy data sets. We can look at sediments. We can look at the geological record and get a really good feeling for where and when places were underwater, how sea level has changed, and so forth. Today, we have much more modern technology. On the left, we have, this is a photograph of an observing station. NOAA and its partners have observing stations, not only all around the United States coastline, but in many other parts of the world, where we monitor daily tidal changes, and then we can average together to produce what we call a mean global sea level. So we can take the averages of sea surface height over long periods of time, say 30 years or 100 years, and then we can come up with a long-term average. And then anything that would be a deviation or a departure from that average, we can call change or an anomaly, and that sort of thing. More recently, since the period of the early 1990s or so, we have been, the surface station observations are being complemented by space-based altimetry. Basically, what's happening here is satellites are bouncing lasers off the surface, and since we know very precisely the speed of light, we know how much time then we can measure very precisely how long it takes that light to travel to the surface and bounce back to the satellite. And we can then measure pretty precisely, to within a centimeter or so, what is the sea surface height, what's the land surface height as well. And so when we compare the two, we can begin to get a feeling for, are these data sources in good agreement? So what you're seeing here, for example, in this solid green line, with the green shading on either side, would be a global mean sea level average. So what you're seeing is the mean value, but there's some margin of error as we've averaged these stations together. The margin of uncertainty getting smaller as we go forward in time. We have more and more modern instrumentation around the globe, so our confidence is going up on that range. And then this gold line here is showing you the satellite altimetry record superimposed on the tidal station data record. And where they have very good agreement, you can see then we have pretty high confidence that we're understanding what is the change in sea level over time. So a key point, one of the takeaways for you all today is that global mean sea level is rising at an accelerating rate. And you can see what that rate has been for these different periods of time. In the early 1900s, a little over 0.5 millimeter per year, going up to roughly double that in that 60-year span or so from 1930 to 1992. Then almost triple that in that period from 1993 to 2015, and then again an increase from that period 2010 to 2015 up to now over 4.4 millimeters per year. So we can see that the curve is bending and it's bending upward. And so you might be saying, well, why is this happening? Well, it's a combination of factors, but primarily the melting. I like to say our frozen assets are melting. Particularly glaciers in the northern hemisphere, as well as the ice sheet on Greenland, the ice sheet on Antarctica. As that water melts, it goes into the ocean. That's a direct, unequivocal relationship. And of course, as our world has been warming over the last century with an accelerating rate in the last 40 years or so, a lot of that warmth, the large majority of that energy imbalance being taken up, like over 90% of the energy imbalance is being realized in the ocean. And so as things warm up, they expand, and that thermal expansion is another driver of sea level change. So, and this is just a chart. I really like this. It's a great way to just sort of visually portray what's been happening. So the about half of that rise from the period of from 2002 through 2014, about half of the sea level change due to thermal expansion, and then about the other half from melting occurring on Greenland, glaciers in the north, well, throughout the world, most of them in the northern hemisphere, and some melting on Antarctica as well. So it's important. You'll notice I've been using this term global mean sea level, and that's not necessarily a reflection of what's happening at any given location. So here is a map taken from the NOAA Tides and Currents website, and all of the visuals throughout the presentation, I've given you credits and links to where you can go if you want to go to the source and learn more. But here we have a map showing you, and you'll see along the North American coastline arrows, and it's color-coded. So everywhere that the arrow is pointing upward, that means sea level is rising. And the longer the arrow and the more it graduates towards red, the larger the rate, the higher the rate in terms of millimeters per year. So for example, if you're concerned right here at, say, Louisiana, where the Mississippi empties into the Gulf of Mexico, they're experiencing sea level change, relative local sea level change at a rate of about 9 millimeters per year. So much greater rate than the global mean. Up along the mid-Atlantic, for example, I'm here just west of Annapolis, where I live, but the mid-Atlantic region is experiencing one of the fastest rates of relative local sea level change. And so in this area, along, say, the Chesapeake Bay, in this area, say, along the Louisiana coastline, you've got the double whammy of sea level rising, but land is sinking. It's called subsidence, the land subsiding. So those can be reasons. And then there are other factors having to do with current patterns, having to do with temperature patterns, having to do with airflow patterns, and so forth, that can also change the relative local rate of sea level change. But you'll notice, for example, in parts of, say, the Pacific Northwest, the southwest coast of Canada, the northwest coast here, and the southern coast of Alaska, for example, we've got down arrows. And not only that, but big down arrows. So more than, so in this case, relative local sea level is going down. And you might say, well, why would that be occurring? How's that possible even? Well, In some places, the land is rising at a rate much faster than what the sea level is rising. So it's a relativistic perspective. So if the continent is still rebounding from the last glacial maximum, so back, tens of thousands of years ago when there was a vast ice sheet sitting on top of North America, extending well down, say past the Ohio River Valley, for example, and in parts of Kentucky, we had this ice sheet. So you could see where it would have been weighing a lot and sort of pressing down on the land. So there's been some rebounding, shall we say, where the land's still rising. There can also be other factors like tectonic uplift. As one tectonic plate is moving under another one, it's causing uplift. And so that can be a factor in some locations as well, where it's causing the land to rise or uplift at a rate today currently greater than the rate of sea level change. So it's important to keep in mind where exactly are we talking about in terms of considering, well, what could be the local impacts of sea level change? What's the urgency of the issue for this particular location, and whether or not we should take action? So these are factors to keep in mind. In many places around the US and in other parts of the world, we have been seeing sharply increasing incidents of what's called high tide flooding. Sometimes it's called nuisance flooding. Sometimes, whoops, that was weird. Sometimes it's called sunny day flooding. But here are a few snapshots from some parts around the US in Charleston, South Carolina, for example, Annapolis, Maryland, Miami, Florida. You can see that these are sunny days. Well, this is not a sunny day, but there's no major event that was really happening other than the fact that the mean high water level overtopped a threshold. And now we have seawater. We have salt water encroaching in areas where we did not originally intend for it to go. And so here, for example, this is just east of where I live in the waterfront community of Annapolis, Maryland. And this is a business district and a tourist district. This is where they have the Annapolis Boat Show, for example, a lot of restaurants and so forth there. And so we don't really want, ankle deep seawater along the sidewalk and the streets here in this area because it's not good for tourism and business. Here's a housing area in Miami, another housing area in Charleston. And so we don't really want ocean water or seawater in our streets here because salty water, splashing up into our engine pan, the axles, it can wreak havoc. So the number of days per year in which this is occurring in coastal communities around the US and other parts of the world are dramatically increasing. And so that's a part of the issue. That's the part of the sort of why do we care? And so if we see that that is now occurring, and we know that we're in a global warming trend, and we know that Earth's frozen assets are melting, well, what do models project? These are a couple of maps I lifted out of the most recent NOAA technical report. This is actually an interagency report, but it's the lead author would be colleagues here in NOAA, but joined by the U.S. Army Corps of Engineers and NASA, the U.S. Geological Survey, and other researchers came together to author this report. And what you can see here are two different scenarios and what the models are projecting for North America with Alaska and Hawaii, and then parts of the Caribbean in an intermediate, what's considered to be a intermediate low emission scenario by the year 2050. And what's kind of concerning here is if we recognize that mean global sea level rose by not quite 1 foot over the course of the 20th century, well, it's a little bit sobering to consider that it could rise by that same amount again in just the next 30 years. So if you look at much of the US East Coast line and all around Florida, for example, models are projecting at least another 12 inches of sea level rise in the next 30 years. The Gulf Coast, even higher, as much as 18 inches to 2 feet of sea level change, again, due to the combination of changing sea level and sinking lands, and same along, say, right at the mid-Atlantic, a higher rate of sea level change locally due to the subsidence. Here's another interesting thing to note. Here we are in the intermediate high emission scenario, not the highest emission scenario, but if we continue to emit heat trapping gases such as carbon dioxide, which is of greatest concern, at the rate or at an increasing rate over that next period of time, then we can see that the models are projecting an even greater rate of increase of mean global sea level. So the eastern seaboard and all around the Florida coastline, for most of the Florida coastline, as much as 18 inches of sea level change during that span of time, parts of Hawaii as well. So again, it's a big concern, and there is a reason to be sitting up and taking notice. In the Climate Explorer, which is one of the main online tools that we offer through the U.S. Climate Resilience Toolkit, which I threw up on screen a moment ago, that we have the Climate Explorer, which we give downscaled projections for every county in the U.S., as well as about 90 observing stations along the coastline. So here I chose for Annapolis, Maryland, for example. You can see here in these gray bars what has been observed in terms of the number of days per year with high tide flooding. But as we go out through the course of this century, you can see what's being projected at that observing station at a little over half a meter. So that threshold is about a half meter over mean high water level. And so basically you can see this is a lower emission scenario in blue, higher emission scenario in red. And so what that's telling us is that the number of days with high tide flooding could be increasing, or could be as many as 42 to 100. That's like 1 out of 4 days per year, more than 1 out of 4 days per year, where we're experiencing high tide flooding in Annapolis, if that scenario comes to pass. Here's a West Coast station in Washington State, a location known as Toke Point. Again, you can see what has been observed, and then again, what the models are projecting. In the lower emission scenario, 22 days, but in the higher emission scenario, as many as 40 days per year with high tide flooding at that location. And so if you're interested, I've given you the URL where you can go and interact with the Climate Explorer and learn more and access these data and these charts. So in short, this is showing you the range of what's plausible. That's what climate projections are a look at what is plausible, given certain, understandings. But the biggest wild card, I think, in terms of which outcome will we see decades into the future, really has to do with what choices will humans make in terms of our rates of emission of heat trapping gases. That's why there's these ranges. That's the difference between a projection and a prediction. This is just simply plausible scenarios based on the physics, but given particular assumptions about the emissions scenarios. What could it look like by the year 2100? So here is a chart, again, showing you what the historical estimates were, what was measured by tide gauges, complemented by the satellite record here in green, and then this cone and that range of uncertainty. Models are projecting in this resource, a range of anywhere. This is considered to be a very conservative estimate, at least 1 foot to 4 feet. So that orange bar is what is described as the high confidence range that scientists have. But these gray shaded areas show what could occur. And what's really interesting to note is if we don't assume rapid loss of ice on the ice sheets of Greenland and Antarctica, then it might stay down in this range. But there's no reason why it couldn't be significantly higher up into sort of the 6 foot range if we were to see significant acceleration of melting on, say, Greenland and Antarctica, for example. But so this is what could happen if we lift our gaze a little further out through the course of this century. Just to put that a little bit into perspective, it's important to note that when we talk about global warming, we're generally reporting an average global temperature, but everywhere is not the same. And if you look at this false color map, this anomaly map showing you departure from average, for this period of time, you can see that not everywhere is warming at all times, and that some places are warming more than the others. But overall, when we look at a long-term trend line, you can see, according to this orange line, that the Arctic is the fastest warming region on Earth. I don't know why it keeps doing that. And it's warming at a rate of about twice as fast as the average global, the global average. And so the Arctic, in short, is true to say that region is the fastest warming region on Earth. And so, well, why do we care? Well, the old saying, what happens in Vegas stays in Vegas. Well, the reverse is not true in the Arctic. What happens in the Arctic doesn't stay in the Arctic. And so if we look at this map showing average surface temperature, and we can see that the temperatures are greatest, the temperature anomaly is greatest over land. We know that encircling the Arctic region in the high latitudes of, say, Alaska, North America, Europe, and Asia, what's known as the boreal forest, this vast evergreen forest. And through most of the year, the soils of those ecosystems are locked or frozen. But we've been seeing the thaw line moving farther north, and we've been seeing the time of year where they're above freezing and therefore thawing out, getting longer and longer with each passing year, with each passing decade. And so over geologic time, this ecosystem has been a large sink of carbon. So in other words, as these trees and plants are photosynthesizing, they're drawing carbon dioxide out of the atmosphere, fixing that CO2 in plant structures, leafy material and woody material as these plants grow. And of course, when they die, when leaves fall to the ground, they settle into the soil gradually over long periods of time. And in places, this is a very carbon-rich soil. You can see in places tens of feet thick in some places. And as it thaws out now, what's happening? Well, those microbes in the soil are doing what they do. They're decomposing the organic matter in the soil when they thaw out. And what is a byproduct? Well, a byproduct of that decomposition is methane, which is a very potent heat trapping gas, carbon dioxide. And so we observed an interesting reality. This was published, new research published by NASA some years ago, showing that in the period 2003 through 2017, that ecosystem flipped from being a net sink of carbon to a net source of carbon. In other words, more carbon now being given off by that ecosystem due to the decomposition in the soil than is being drawn down during photosynthesis. So in short, it's like Mother Nature has now, we've crossed a threshold and Mother Nature has put her foot on top of ours in terms of putting more heat trapping gas into the atmosphere and at an accelerating rate. So and that's called a positive feedback loop. So as we warm the planet, we cause more and longer thawing periods. And as we thaw the permafrost, more heat trapping gas escaping to the atmosphere, causing more warming. And there you see how the positive feedback loop works. And so again, and also then another way what happens in the Arctic and in the Antarctic doesn't stay there. Well, the more we're losing ice off of the vast ice sheet of Greenland, it holds about 9% of the fresh water on planet Earth. Well, where does that water go as the ice sheet is melting? It goes right into the ocean. It's driving sea level change. And of course, the sea ice, as the polar cap is shrinking, more sunlight, therefore penetrating into the ocean, more of that heat energy being trapped and contained in the ocean, over 90%. Has been over the last half century or so. And so those are drivers of thermal expansion. But as we progress through the course of this century, it's expected that the melt of the ice sheets on Greenland and Antarctica is going to dramatically increase as compared to the thermal expansion problem. And that's going to be that primary driver of sea level change through the course of this century. And so, but there is a wide range of uncertainty, and that does kind of come back full circle to, well, what is going to be the sum total of human choices? How much action will we take to curb our emission of heat trapping gases in the atmosphere? And then, of course, what are going to be some of those other tipping points in the climate system that could lead to other abrupt changes. So these are some interesting science questions to stay tuned to. But it's also important to keep in mind, if we zoom in on any given location, that sea level rise is only one of a number of factors. So consider a coastal city. This could be any city. This happens to be a photograph of a European city, but sits right on a water that's very near the mouth of the ocean. And there's sort of several things that might be occurring, but you could imagine your city. This could be a city in Florida. It could be a city in the mid-Atlantic, or even on the West Coast, where you might have a very strong, say, hurricane or a very strong low pressure system bringing lots of rain. So you could imagine, say, the bands of one of the hurricanes reaching very far inland and dumping lots of rain. Well, that rain, eventually it's falling on what is increasing impervious surface area. That's one factor. And then as you have, consider the Chesapeake Bay region, and you've got some of these bands of rain coming well inland, very far to the west. Well, as that rain falls inland at the high ground, where does the excess stormwater and rainwater run towards? Well, back down towards the coast. And you might have, in addition to what's falling locally, but what's also running in from points west, but then on the other side, you might have a very strong wind flow pattern, the storm surge being driven by the very strong winds. And so it's pushing seawater at the coast. And then if there's been an increase in groundwater level in some of those other places, you begin to see like that quadruple whammy. So during these extreme events, you can have drainage systems completely overwhelmed. And we have seen that now more and more, ranging from Superstorm Sandy that hit the New Jersey and New York area to any number of other major hurricanes that were creating these problems. So we see that there's more rain falling in these hurricane events. Why? Because a warmer atmosphere has a greater capacity to hold more water vapor, A, and B, a warmer ocean gives up its water more readily to a thirstier atmosphere. So these storms, even though they might be, it's only a Category 2 or a Category 3 storm in terms of its wind strength, it's carrying way more water. And so that's an important thing to keep in mind, especially for these coastal communities that might be suffering from that quadruple whammy of water kind of coming from all angles. Something else to keep in mind as we consider the resilience of our communities and cities along the U.S. and other countries around the world along the coastline. So again, sort of addressing the question, why should we care? And I've given you a link to this website. This is NOAA's Office of Coastal Management. In the United States, they're predicting that over 106 billion worth of coastal property will likely be below sea level by the year 2050. So that's a major hefty price tag there. Over the next 5 to 25 years, greenhouse gas driven temperature rises will likely require construction of new power generation plants, and that could cost billions of dollars per year. The U.S. coastline, as I showed you on that map, is projected to rise 10 to 12 inches in the next 30 years. And as we saw, that's going to vary as a function of exactly where we're talking about. It's going to be different in different locations. So there's factual information here on this website. And I want to quickly transition, though, into the next section. I'll move a bit more quickly through this in terms of, well, what can we do about it? We don't just have to sit and watch it happen. The good news is we understand the problem, we understand the causes of it, and we have really good tools for predicting and projecting its rate of onset. So, and we do know that there are strategies and response options that we can take that can help us mitigate and or adapt to the problem. So that's what this section is designed to do, just sort of at a high level in terms of helping people be conversant with these terms. Quite often we'll hear the term mitigation, often in the context of climate change or global warming. The term mitigation is used specifically to refer to reducing emission of heat trapping gases like carbon dioxide or removing them from the atmosphere in order to slow the rate of global warming or even eventually stop it and thereby reduce the harmful impacts of global warming. So I like to say mitigation are actions to avoid the unmanageable. There are scenarios in the future, wide differences when we get out towards the end of the century in terms of outcomes, in terms of temperature and sea level, where some scenarios are much more desirable than others. And so we do still have some ability to manage that. And so there are some scenarios that are less manageable that we'd like to avoid. And then another category of response options are generally called adaptation. And that's referring to actions we could take that are improving our ability to cope with or avoid harmful impacts by taking action to reduce our vulnerabilities, to reduce risks, and where possible, even exploit new opportunities that some of these changes may be bringing. So I like to say then adaptation is a complementary, it's not either or, I think it's both and, but adaptation is complementary to mitigation actions in terms of allowing us to manage the unavoidable. Look, we know that there are extreme events also caused by oscillating patterns in the climate system, like say El Nino, La Nina, and other oscillating patterns that are going to produce extreme events or rain rivers with or without global warming. California, for example, has suffered from some of these rain river events, bringing heavy, heavy rain amounts along its coastlines. And these would occur with or without global warming. Now, they may be made worse because of the fact that a warmer atmosphere can carry more water. But the point is, we still have to be able to manage these unavoidable events. And it's also part of the problem is, more people building more in harm's way. So there are these unavoidable extreme weather and climate events that are going to be occurring, which is why I say both are needed, and we need to be conversant in both categories of response options. So this is not intended to be an exhaustive survey of all the things that we can do. There's quite a lot of it. We could spend whole sessions talking about strategies and the pros and cons. But just in terms of, helping to fill in some of the blanks, what are we talking about? Well, for example, we can develop habits to reduce our energy consumption, and by consuming less energy, especially where those are requiring or drawing upon, say, fossil fuel burning, coal or oil or natural gas, reducing our consumption will reduce our emission. We can also consider switching to carbon-free energy sources such as solar, wind, geothermal, hydro, and so forth. So there are energy sources that are much less carbon intensive than, say, burning coal or fossil fuels. I'm a big fan of the strategy of planting trees to increase the amount of uptake of carbon dioxide. But this can offer co-benefits, especially in some of our urban environments, to help reduce the severity of urban heat islands. By shading the surface, by evapotranspiring, they can help to cool the surface, especially in our cities and inner cities. And where there's more green space, it can help slow down the water that falls in these very heavy rain events, helping to somewhat offset or reduce the severity of flash flooding. So there's any number of good reasons to consider tree planting. And then there's been several proposals by different groups, such as the Rhodium Group and their report called Risky Business, calling for a carbon tax and dividend, where people might pay an amount to pollute carbon into the atmosphere that could go into an escrow account, and an annual dividend check gets paid out to all Americans. So they don't want to call it a tax. They want to call it a carbon dividend. But ultimately, their goal is to build the costs of polluting into the economy so that we can begin to have hooks and handles for grappling with the problem in the economy. So these are a range of different types of mitigation strategies. There's plenty more we could talk about here, but I think maybe you get the point. And again, adaptation, anticipating and adjusting to new conditions. So we can begin to assess a location's ability to handle things like extreme heat or extreme high sea level with storm surge. So what can we do specifically in our communities? Well, we can consider elevating structures and or hardening them and or retreating from the shoreline. So there are different options that we could take, but many of these are emotionally charged subjects. we could consider restoring shorelines to their original state or building living shorelines that can offer co-benefits. We have been working with lots of municipal governments, regional governments, state governments around the country to work in co-producing resilience plans, helping them do vulnerability assessments and helping them to co-develop equitable resilience plans for different actions that they could take. So just a couple of other things I'll share before I wrap up, and we can open it up for discussion. Specifically, we can elevate and harden structures. This was from, I think, Hurricane Michael, which hit the Gulf Coast in the Florida Panhandle about 4 or 5 years ago or so now. And this became sort of an iconic photograph where you can see the devastation all around this place. But then look here, this was a cottage on the waterfront. The owners named it Sand Palace. But what was really interesting here, and the case study that they had to tell was, and I've given you a link if you want to go into the Popular Science magazine to read more, and talks a little bit about the construction choices that were made by the engineers and the architects of this building. But they spent about 20% more than they would have. Whoops, I don't know why it does that. Every once in a while, it jumps ahead. They spent about 20% more on the construction costs. But then when you look at the devastation all around it and what is going to be the costs to recover or rebuild some of these other places, they probably came out way ahead. And so some of the things that they did, were to elevate. I think this is about 24 feet higher than sea level. So very high. There's a concrete slab here. They harden. It's a hardened steel roof, which does not blow off the way shingles do. They put in a shatter-resistant glass. So there are any number of design choices that they made here to elevate and to harden, which has clearly paid off in terms of its ability to withstand, stronger, more severe storms and storm surges, which is probably something that we need to consider if we're going to continue to have very valuable property and homes and structures along the waterfront. Again, that sort of so-called, quote, building in harm's way. We like to live where the views are beautiful and where we can enjoy nature and enjoy, days at the beach and vacations. But how can we balance our value for that with, the rising costs of these types of damages and the rising intensity of the extreme events that are occurring? Another option that we have is we can have managed retreats. These can be emotionally charged conversations to have, of course, and it can sort of cut both ways. On the one hand, people don't like to be told, well, you have to move inland, you have to move away from the shoreline. They want to be at the water's edge where the views are nice. But here's a case in North Carolina, the iconic Cape Hatteras Lighthouse. And in this case, it was emotionally charged, but in the other direction, where residents of North Carolina and other parts of the country were very concerned that sea level was encroaching. The double whammy of sea level rise and coastal erosion was threatening this, historic structure. And so a decision was made to bring the lighthouse inland further and to higher ground. And here you can see sort of a before as they were clearing the pathway. Whoops, I keep doing that. And here you can see the track afterwards, the new site to where they moved it, much further inland, much higher ground. And so these are things that we can also consider. And if you want to read there, I've given you an outlink to an article that you can jump in and read a little bit more of the details on relocating the lighthouse a little over 20 years ago. Another option that I favor is the construction of living shorelines. You can think of living shorelines as a category of, quote, green infrastructure. It's basically a term whereby we would use living plants and other structures found in nature like shells or rocks and sand and mud to construct a sort of a living movable barrier, one that can sort of move and flex and adapt as the environment changes around it. And so some interesting statistics, often, especially in North Carolina, where I grew up in Eastern North Carolina, I go to the beach all the time there on boat banks, what's known as Atlantic Beach. My mother lives in Morehead City, just on the mainland across the bridge from Atlantic Beach. So I go there all the time to visit. And but we often see these hard bulkheads, these concrete walls or rock barriers called riprap. And where possible, coastal ecologists are encouraging people more and more to consider these living shorelines because they offer so many positive co-benefits. So a hardened structure can function sort of in one dimension, but they may impact other parts of the ecosystem, other landforms. They may accelerate erosion, for example, in front of them. They may cause other problems. So they don't necessarily offer the co-benefits that a living shoreline does. So, for example, having lots of marsh grass or seagrass, well, it's photosynthesizing. So it's drawing down carbon out of the atmosphere, just the way land plants do. And this can store the equivalent of 76,000 gallons of gas annually, the carbon equivalent of that amount. And so that's an important trade-off alone. But then, of course, they help to trap sediment. And so they can help to build up and replenish the land so it can be a control against erosion. And we know that this is valuable habitat for fish and shellfish to lay their eggs and to grow from juvenile into adult stages. So it's great for that. And we also know that that helps to filter water. So it's providing a valuable ecosystem service by filtering a lot of known human pollutants that may run into the water, helping to filter that out. They can absorb a lot of the energy from strong waves and storm surges to help dampen the effect from, say, strong storm surges. So there's any number of co-benefits and reasons why. And there are these really interesting work parties, and you can find case studies online and see photographs of coastal ecologists with lots of local volunteers doing these coastal restoration projects. And I've got a picture of one right here where you can see what it sort of looks like as they're setting up that structure. That's what this photograph is showing you, sort of planting some of these eelgrass or marsh grass lands. And it's a great way to get people out in the community who might want to roll up their sleeves and be a part of the solution. Just the last couple of things I'll say. Here's a screenshot of the U.S. Climate Resilience Toolkit. It's online at toolkit.climate.gov. And there's a section called Case Studies. And you can click the button or the link here in the nav window. And as you can see, we've got well over 150 case studies from all around the country now, many of them along the coastlines. So here's one looking at a place in Ventura, California, where they had to do a managed retreat to manage the shoreline at a place known as Surfers Point. And so you can click the link there and go in and read the case studies. And so we've got lots of case studies from around the country of people taking action to protect people, property, infrastructure, and natural resources from weather and climate extremes. Where else you can go to learn more? There's the sea level rise technical reports freely available online. I've given you the link here. NOAA's Office of Coastal Management has a digital coast. It is just chock full of interesting data tools and additional case studies and information that's science-based. And so just in wrapping up, with that, I'd like to just put a pin in it for now and open it up to hear from you. So I'm going to stop sharing for a moment and then just come in and just enjoy the conversation.